Welcome. Today we are discussing our strategic roadmap transitioning from structured multilingual meeting translation to real-time duplex care communication. Phase 1 is our already validated pipeline, which handles one-to-many translation for meetings by processing audio through speech recognition, large language model translation, and synthesis. However, moving to Phase 2 requires us to cross a critical evolution boundary. In caregiving, communication must be a low-latency, duplex experience. By optimizing WebRTC transport, streaming TTS, and voice activity detection, we aim for a round-trip latency of under 1.5 seconds while carefully managing risks like dialect variation and network jitter. Let's look closer at Phase 1, which validates our core components. Because meetings can tolerate a latency of 5 to 15 seconds, we process audio using a sliding chunk method, capturing 20 to 30 seconds of speech with a brief overlap to preserve context. We then apply specialized terminology dictionaries and prompt engineering to standardize medical terms before translating. The text is finally converted into multiple target languages using streaming TTS. This pipeline is highly scalable and cost-effective, though we continue to actively manage risks such as speaker diarization and term alignment to maintain high-quality outputs. In Phase 2, our focus shifts to low-latency, duplex dialogue designed for direct caregiver and recipient interactions. Unlike meetings, a natural conversation cannot tolerate delays, so we target an end-to-end latency of under 1.5 seconds to prevent turn-taking collisions. Using WebRTC for real-time transport, we process bidirectional streams supporting Mandarin, Taigi, Indonesian, Vietnamese, and Filipino. Because care environments are often noisy or suffer from unstable networks, we're designing resilient, low-complexity interfaces. This system will be deployed on split-screen devices and paired wearables to ensure smooth, immediate communication. To achieve this, our system architecture must evolve from chunk-based processing to continuous streaming. In Phase 1, we process speech in large asynchronous chunks. While this preserves context, it introduces too much delay for natural conversation. Phase 2 replaces this model with streaming agent architecture. Here, small audio frames of 20 to 60 milliseconds are continuously sent to a voice agent orchestrator. We reuse our validated translation prompts and terminology dictionaries, but shift from batch processing to continuous frame-by-frame streaming. This architectural shift is key to reducing latency and maintaining natural conversation flow. Finally, our staged implementation roadmap is structured to progressively reduce risk. We begin with Milestone 1, establishing our meeting translator to validate chunk-based processing. Next, Milestone 2 focuses on building robust evaluation datasets for local dialects like Taigi. Milestone 3 integrates WebRTC and LiveKit to prototype our streaming pipeline and voice activity detection. This culminates in Milestone 4 with real-world care pilots on tablets and wearables. By systematically scaling from structured meetings to instant dialogue, we're laying down a solid, high-performance foundation for the future of automated multilingual healthcare communication.